In this video, we're going to learn about molecular geometry and valence shell electron pair repulsion theory, also known as VSEPR theory. So VSEPR theory essentially tells us that electron-electron repulsion will result in there being a maximized distance between electron domains. What is an electron domain? Well, if we consider a molecule like carbon doubly bonded to oxygen with two singly bonded hydrogens, this is formaldehyde, and I've drawn the Lewis structure for it. If we look at the central carbon atom, well, the central carbon atom has three different groups attached to it. One is the oxygen, and one is the hydrogen, and one more is the other hydrogen. Now, I know that the oxygen is doubly bonded. And yes, if we're talking about the octet rule, then there are 4 electrons involved in bonding between the carbon and the oxygen. But that is a different consideration from molecular geometry and the electron domains. Here we just say there are 3 atoms bonded to the carbon and no lone pairs. Now, if we were to look at the oxygen has 3 electron domains because it has 1 bonded atom, the carbon. It also has 2 lone pairs. And so you can say that there are 3 electron domains around the oxygen because there are 3 places where electrons are. And when you think about it, electrons are all negatively charged, so they will repel each other. And so that's why we get a maximized distance between different electron domains. So when we look at what is attached to this carbon atom, we're going to get a maximum degree distance between in that hydrogen carbon oxygen bond angle. So getting to a definition here, an electron domain is a bonded atom. And again, this is regardless of whether it's singly, doubly, or triply bonded, or lone pair. Nice and simple. A bonded atom or a lone pair counts as an electron domain. Now, if we're looking at this molecule, with respect to the carbon, this is going to be flat. And you can look at it as though you have a circle with 360 degrees. This bond angle is going to be about 120 degrees. This bond angle is going to be at 120 degrees. And this last one is also going to be 120 degrees. We get a circle, 360 degrees. Now, valence shell electron pair repulsion can get a little bit more complicated. What is nice about this molecule is that it is flat with respect to the carbon. And so it does make it a little easier to see because it's two-dimensional. But we'll get into the complexities more in a little bit. So if we look at BeH2, beryllium is a group 2 element. It forms only 2 bonds. And this is one of those weird cases where there's a molecule that doesn't have its octet. But if we look at this, you kind of want to draw it with the perfect geometry where the hydrogens are opposite each other. And just as in the previous case, this is going to be a 180 degree bond angle because there are only 2 electron domains around that central beryllium. CH2O we already did. We could also look at NOCl, nitrogen, oxygen, chlorine. I'm sketching these out very quickly, but you would draw these Lewis structures 2, 4, 6, 8. You would draw these Lewis structures the same way that I've taught you. This nitrogen also has 3 electron domains. We've got the nitrogen with a lone pair, that's 1. With a chlorine atom, that's 2, and the oxygen atom makes a 3rd electron domain. So actually the bond angles here should be similar to the bond angles in CH2O that are around the carbon. I will point out that lone pairs cause a little bit more repulsion than bonding pairs. So although all three of these angles are going to be pretty much spot on the 120 degrees, we'll find that these are a little bit less than 120 degrees. How much less? Not much, maybe 117, because that lone pair pushes a little bit harder on the bonding electrons NCl and the bonding electrons NO. Now, things get a bit more complicated when we get to, for example, CH4, because this is a three-dimensional structure. And I just want to point out that if we were to say that these are all 90-degree angles at, a bunch of right angles, then that wouldn't be optimizing the distance between them, because we're not even considering the fact that this hydrogen and this hydrogen are separated by 180 degrees. We're missing the third dimension going into and out of the page here, or the board here. So what we would have to do is make this into a three-dimensional shape called a tetrahedron, which you're going to see more of in just a moment. But when there are 4 electron domains, that wedge here means it's kind of coming out of the screen, and this dash means it's going into the screen. And this way, the bond angle from hydrogen, carbon to hydrogen, from this hydrogen to this carbon to this hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen, all of these bond angles will be exactly the same. They will be 109.45 degrees, but I'll round it to 109.5 degrees. In the case of NH3, we're going to look at this where there's a lone pair on the nitrogen. And because of this lone pair, it is making it somewhat asymmetrical, not the same as the CH4 where every bond angle is the same. Because this lone pair pushes a little bit harder, we're going to have bond angles that are slightly less than 109.5. This is about 107. And in the case of water, where there's 2 lone pairs, this bond angle is going to be about 104 degrees, maybe 104.5 degrees. I think it's 104.5 degrees, but what I would say, like what I would expect from students here, is I would expect this to be written as less than 109.5 degrees. So here we've got a case of 2 electron domains, we have 180 degrees. We have 3 electron domains, and this is going to be 120 degrees. If there's a lone pair, it's slightly less. If we have 4 electron domains, it's about 109.5 degrees. If you have lone pairs, that makes the angles a little bit smaller. Now, if we are trying to name the electron pair geometry or the molecular geometry, we need to first draw out the Lewis structure and understand the number of electron domains. And then we need to consult a chart that we have here. Now, I'll make this nice and simple. Electron pair geometries, it doesn't matter whether we're talking about lone pairs or bonding. Just the steric number. The steric number indicates the EP, the electron pair geometry. So what I mean by this is if we look at CH2O and NOCl, both of these have 3 electron domains. So their electron pair geometry they are both the same electron pair geometry. And for them, we will look at this chart right here. We will see that the steric number is 3, and it is going to be trigonal planar. Trigonal planar, so we say the electron pair geometry is trigonal planar. But if we're looking at the molecular geometry, then we have to consider the number of bonds or bonded atoms and the number of electron pairs, like lone pairs, I should say. So consider numbers of lone pairs and the steric number. So what I mean is we can refer to our chart, and in the case of the CH2O, which was here, there are no lone pairs. And so if there are no lone pairs, we will say that the molecular geometry is the same as the electron pair geometry. It is trigonal planar. Trig pull, I'm going to write just to abbreviate it. But in the case of the NOCl, there are 2 electron domains that are bonding, that are atoms to which the nitrogen is bonded. There is 1 electron domain that is a lone pair. So we go back to our table and we see that for a steric number of 3, when there is 1 lone pair, the bond angle is less than 120 degrees, and we have a bent or angular molecular geometry. So I'm going to say that the molecular geometry, geo, is bent or angular. But I'll just write bent here. Now, in the case of CH4, NH3, and H2O, well, for all 3 of these, they all have 4 electron domains. In the case of CH4, there's 4 bonding atoms. In the case of NH3, there's 3 bonding atoms and a lone pair. In the case of H2O, there's 2 bonding atoms and 2 lone pairs. But the steric number is 4. Now, if we look here, if we have a steric number of 4, the basic geometry is tetrahedral. So what we will say is that the electron pair geometry, geometry is tetrahedral. And because the CH4 has no lone pairs, its electron pair geometry is the same as its molecular geometry. So the molecular geometry for CH4 is tetrahedral. For NH3, we have to look on this chart again. We have a steric number of 4, but there is 1 lone pair. We will call this trigonal pyramidal. This is going to be trig pyramidal, again with the molecular geometry. And in the case of H2O, we have 2 atoms to which the oxygen is bonded, the hydrogens, and then 2 lone pairs. So it's 2 and 2. And we go to steric number of 4 with 2 lone pairs. This is also considered bent or angular, but the angle is 109 degrees, or just a little bit less than that. So this is bent. We could also consider, if there's a steric number of 5, then you will have essentially around the central atom, if there are 3 groups around it, and then one above and below. The three that are around it are essentially trigonal planar, but then you have in the vertical domain, you have linear. So it's kind of a combination of the trigonal planar if you're looking around here, and then linear with respect to here. So you'll actually get two different bond angles, and that's why you see the 120 and the 90. And of course, lone pairs will affect the angles. We also have octahedral, which would be if there are 6 electron domains, and that would just be if you have essentially 4 that are separated by 90 degrees that are in the same plane, and then vertically there is another linear component that is 90 degrees separate from the horizontal, we call these the equatorial domain. But these are less common. An example of something that's octahedral would be SF6. An example of something that's trigonal pyramidal would be like PCL5. So I hope this video has been helpful to you. Let me know if you have any feedback or comments in the comments section. Thank you.